We can start the recording also. Oh, hello everyone, and welcome to this module on smart grid communication course. So we will continue our discussion on introduction to TCP-IP. Well, last week we went through the layered architecture of TCP-IP and we put everything together. This week we go more on the programming's view, the transport layer, and also some performance aspects. Oh, and a small reminder, well, we said that we have an end-to-end principle. We run the application layer and transport layer only on both ends of the communication. And the intermediate packets only go through the network, link or MAC, and physical layer just to carry the packets, for the routing reasons. Well, transport layer is what translates what human understand to something that network understand. It's basically make network services available to applications. As I said, it's only on this end system. We do not go through the application layer or transport layer in routers. And we talk about the two main transport protocols, UDP and TCP. Oh, UDP is the least that you can get, is the minimal transport protocol that you can use on the internet. It only provides you a transport protocol that sends, well, in a sender point of view, you provide a message to UDP and it only sends it for you. It does not care about this message is received or not, whether if you send several consecutive messages, whether they are received in order in the receiver. In the receiver point of view, you only wait for an incoming message and you receive it. Whenever you receive it, you do not care whether it is in order, whether it's a part of some consecutive messages. You will deliver it to the application layer. Just the sending and receiving commands is the minimal service. With TCP, we do more. We do error recovery and flow control. In TCP, we care about errors. We solve this problem. If there are errors, TCP will detect them and will take care of them. Will recover lost packets by do some retransmission. And it does even more. It has flow control. We'll see today what that is. The first thing to notice is that we do not have TCP v6, TCP v or UDP v6, UDP v4, TCP v4. The transport layer is also independent from IP. Whether you're using IPv4 or IPv6 doesn't change the TCP or UDP that you use. The software is changed for sure. Well, the space of IPv6 and IPv4 are not compatible. They're using this different numbering. Well, the software is for sure is changed, but the principles of TCP and UDP are the same. Well, UDP, same as TCP, use port numbers. So we already saw that port numbers are everywhere. Port numbers are the thing that we use in the NAT boxes, in the network address translation boxes, to cheat, to reuse some, reuse the same IP addresses, private addresses several times. So that's thanks to the port numbers. The reason that we have port numbers is that, well, on this computer and host A, there are several processes running. Well, incoming packets it belongs to one of these processes. For example, at one point, you want to ask a DNS server, what is the IP address of this website? And you're also doing a video streaming on another side. Well, there are two UDP processes running in parallel, and your computer needs to distinguish between those two. All those packets coming from a DNS server or a streaming website that you're looking or belongs to your IP. Well, it will be cached by your computer. Then it's time to check whether it belongs to which of these processes. That's by using the port numbers. So your computer, when it creates a UDP connection or a TCP connection, gives your operating system gives a valid port number to each process, and that's used to find the corresponding process for the incoming packets. Same thing at the destination. Whenever you're sending data to a server to another host, you need what is the port number at the destination. You need two pairs of information. One is the source IP and destination IP addresses, as well as the source port number and the destination port number. Yes?
Is there a default size for the port number?
default size? Well, I don't know how many digits exactly, but the thing is the port number is given to you by the operating system, and the operating system checks what is available at your computer. It's not the case at the servers. We'll talk about it. But the servers will use well-known port numbers, and we will see in a minute why. And if you look at the UDP header, you see UDP source port, UDP destination port, as well as the IP address and destination address. Well, this is what I've explained there. Let's fix one thing. Well, we use the word server several times. We are saying DNS server, we are saying mail server, web server. Well, what does that mean in our context specifically? So I invite you to join the SPCUP. Or if you do not have the application, you can use the web.spcup.info, and this is the room key. And I will open this file. So I close the poll in a second. Well, the correct answer is D. In fact, no one has answered D because you are tempted to think of servers as different things. But for us, server is something that waits for requests to come. Server is something that is always online and waits for requests for new incoming messages to come. For example, as mail servers. Mail servers are something that are always online, waiting for incoming new messages. However, in clients, you might get online, send some messages, and you go to sleep, or you become offline. Clients is something for us that initiate communication to a server, and server is always online because a client can initiate a communication at any time. Well, UDP service is message oriented. What does that mean? It means that when you provide a message to UDP and ask it to send it, it will send it as it is. It will not group it with other messages, and it will not break it into smaller pieces. However, there is a maximum size for this message, which is large. It's 65,000 of bytes. UDP uses the destination address, its destination port, source address, and source port. We'll see that. And one good thing about UDP is that destination address can be unicast or multicast. You can send a single message to several users at the same time. Why is that interesting? For example, when you have a subscription to Swisscom and there is a live streaming, you want to send this live streaming to everyone that has this subscription. Then you have a list of IP addresses and you send these to all people, and that's a multicast communication. That is one thing that is missing in TCP and that exists in UDP. We already said that when you send consecutive messages, they may arrive in disorder. It's up to application to fix this in order delivery. For example, if you have a video and you decided to use UDP to send this video might be in several parts and in several messages. And in the receiver, these parts are in order or misorder. It's up to application to fix that. We do playback buffers, and application can fix that to find the correct start and end time of each piece. But in UDP does nothing about it. Same thing for the loss. So if a message is lost, it's up to application to do the retransmission. In the case of a DNS server, if you send a DNS request and you do not receive a DNS response for some reason, it's up to application to send another request. Or UDP does not do the retransmission itself. We are saying that UDP message, well, we send with UDP, we send a message. It's a message-oriented thing. But in IP, it's a different story. In IP, we have most of the time a maximum packet size. It is 1500 of bytes most of the time. And an IP packet cannot be larger than that. Meaning that at IP layer, we might do some fragmentation. We might break some message into several IP packets, but that's hidden from UDP and application. That's yet another thing that UDP does nothing about it, but other layers must do something about it. For example, if fragmentation is needed, it's done at IP layer, not UDP. We already said that in transport layer it provides a programmer's point of view, and this programming point of view is using a socket library. Here I'm showing a small example of a client that sends one message to a server and then dies. Well, it's a very simple example. And this is a Python version. It's a high-level programming, which we do not care about all the details. If it was in C, we might write several more lines here also. Well, let's start with the server side. Well, at the server side, you create a socket first, and then you bind it. What does that mean? You bind it. Well, you bind it. You give this socket number. We assign this socket number to a specific port. Why do we do that? Well, because we said that if two machines want to communicate with each other, they need the IP addresses as well as the port numbers. Well, if none of them knows the other's port number, you never can start a communication. That's why at server side, we make everything as well known. We make everything visible at server side. We know what is the IP address of the server. If a DNS is already configured in your computer, if it's another website, you can ask DNS to what is this? What is the IP address of this website? Also, we make this port number of the destination available. For example, DNS servers reserve a port number of 53. Whenever you want to send a message to DNS server, you use the destination port 53 because that's what DNS server uses. That's this bind means. On client side, however, it's not necessary to do. Well, as a client, you do not care about this port number. It's just something that at the transport layer to distinguish between processes, for example. So you leave it, you leave it, and the operating system gives you an arbitrary value that is available. So the port number of clients might change. What we try to do not this. So in the server side, we try to do a same port number for a specific servers, and they are fixed. Then at the server side, when you bind this socket to a port number, you do receive from. It's a blocking argument, meaning that when at the server you run this command, it blocks, it hangs. You do nothing. It just waits for incoming messages. Whenever there is a message, it will start reading the message, receive the message, and again comes to this blocking argument. On the client side, well, we create a socket. You leave it up to it's up to now to the operating system to give you a valid port number, and you do send to command. What is send to command? Well, you say what are the destination addresses? Well, you use the IP address of the destination, the port number. If it's a DNS, the port number is 53, for example, and a message. What is the message that you want to send? In the case of DNS, you say what is the IP address of this guy. It is also a blocking, so you do some sending until you're finished. In this example, as I say, it's a simple example. We send one message and we will die, and then we will close this socket. First thing to notice, in UDP, we use what we call non-connected sockets. What are non-connected sockets? There are the sockets that we use send to and receive from commands. It means you can send to everyone and you can receive from everyone. They are not connected. They are not bound to another socket. They are for everyone. In the case of a DNS server, well, everyone can send a request, DNS request to a server. It's a non-connected server. And that's why you have send to and receive from command. We'll see that it's different for TCP. They are not non-connected sockets. They are rather connected sockets. Oh, we said that we do not have UDP v6, UDP v4, but the software is different. Oh, the socket that you create can be in IPv4 socket, or it can be an IPv6 socket. Whenever you want to connect to a website, you can ask DNS what are the things that are available at this website, whether this website provides IPv4 connectivity or IPv6 connectivity or both. This is done by this command here. For example, you can ask DNS about this website here. And the response is, well, there are both IPv4 and IPv6 connectivity. There is a socket with this port number and this IP address. It is IPv4, IPv6 socket. And there is another one, which is in IPv4. This is the port number. This is the IP address. Now it's up to you as client to use the IPv4 or IPv6 address to communicate with this server. If you do not force it to be IPv4 or IPv6, your operating system prefers one. Hopefully it prefers IPv6 most of the time the case. Yes. It means that, well, the UDP transport is the same thing, but the socket that you create for IPv4 communication or IPv6 communication is different. For example, you can call it UDP v4 sockets. When you create a socket, you should mention it is IPv4 or it is IPv6 socket. Well, we already said that we do not have compatibility between IPv4 and IPv6, but there is one good news. If we use IPv6 sockets, it can be used for both IPv4 and IPv6. So we call an IPv6 socket can be a dual stack. How is that? Well, if your computer has both IPv4 and IPv6 connection, means that it has an interface that has an IPv4 address, and it has another interface that has IPv6 address. So we can receive both IPv6 and IPv4 addresses. Then you can use an IPv6 socket for both IPv4 and IPv6. Oh, how is that possible? It's possible because we can map an IPv4 address to an IPv6 address. This mapping is trivial because the space of IPv6 addresses is much larger. It's 128 bits. For IPv4 addresses, it's 32 bits. So we can map exactly each IPv4 addresses to one IPv6 addresses. Well, this is done here. Well, we put lots of zeros and one piece of all one. We fix the first 96 bits. And we have now 32 bits. Oh, that's the IPv4 address. For example, if you want to map this IPv4 address to IPv6, this is the IPv6 version. With lots of zeros and one, and then the IPv4 address put in the IPv6 form. This is what we call IPv4 mapped IPv6 addresses. They are in fact invalid IPv6 addresses. No one used them. They are reserved to map an IPv4 address to this address. Why do we care? Because it makes it possible to use it in the socket library. Or if you have IPv6 socket, now you can use it for both IPv6 and IPv4. It's not at default. So if you have create an IPv6 socket, you cannot expect it to by default support both IPv4 and IPv6. You should modify some options and set them properly. This is how it's done on Linux. Now let me ask you a question. Why cannot an IPv4 socket be dual stack? Yes? Oh, exactly. For the space of IPv4 addresses is much, much smaller than the space of IPv6 addresses. So we cannot map an IPv6 address to a space of IPv4 addresses. We already have a shortage of addresses there, or we cannot also take care of IPv6 addresses. But the other way around is not true. The space of IPv6 addresses is by far larger than IPv4 addresses. So we can use a prefix, a specific prefix for IPv4 addresses. Well, let's see how operating system views UDP. Well, here it's the IP layer, it is a UDP, and the last is the application layer. Well, for example, your computer has both two interfaces, one that supports IPv4, one that supports IPv6. For example, your Ethernet supports IPv4 and your Wi-Fi connection supports IPv6. So you're receiving both IPv6 and IPv4 packets. When you receive an IPv4 packet, meaning that the destination address, it's your address, then your computer look at what is the destination port number. If the destination port number is this one or this one, well, it will provide it to a corresponding socket depending on the port number. And the socket, the first approximation of a socket is a buffer. So when you receive a message, you put it in the socket buffer. And whenever application wants to read this message, it will read it from the buffer. Why do we use buffers for sockets? Well, on the sending point of view, whenever application hands a message to the transport layer, to this socket to send it, the service might not be immediately available. But transport layer is busy sending other things, and it needs a bit more time to send this new message. So it will buffer it for a time, and whenever the service is ready, this packet is sent. In the receiving side is the same thing. The application is busy doing other things, so it cannot read the incoming message at the time that is ready. So we will use buffers, and we put new incoming message in the buffers, and whenever application is ready, can read these messages. That's an example of a dual stack. So you have an IPv6 socket that is used by both IPv4 packets and IPv6 packets, but the principle is the same thing. These are the things that I already explained. Oh, now let me ask you a question. I already revealed the answer, but we'll see. In the case of DNS, we said that we use UDP. We use UDP, we send the DNS query. DNS query is what is the IP address of this website. And the response is, well, this is the IPv4 address of this website. Now I'm asking which one is true. If you do not receive, there is a loss in this communication, what will happen? I'm closing a poll in a second. Oh, the majority says A, which is a correct answer. Well, UDP, as we said, does not care about anything. We will just send and receive some messages. If there is a loss, it's up to application to recover the loss. So in this case, you as an application will wait. If there is a timeout, we will send another DNS query. Let's go through TCP. Well, TCP is more sophisticated. We need to know more about TCP. Well, on internet, as we said, there is a chaos. So whenever you put your information in the form of some packets and you send it to a destination, this packet might be lost. The error might be in a physical layer error. There is a Wi-Fi connection error. There is a physical error, radio error somewhere, or buffer overflow. Well, buffer overflow very frequently happens. Well, we have routers in the intermediate points. It's used by several connections, and sooner or later, some buffers might be full, and it will drop all incoming packets. So that's buffer overflow. That's one of the reasons that we lost packets. TCP is not like UDP. TCP solves this problem once for all. Say, let's have a reliable connection once for all in the internet, and that's done thanks to TCP. Well, what does TCP do? Well, TCP guarantees that all data are delivered. There is no loss. You have a lossless communication. And even better, the data are delivered in the same sequence that the sender sends. So if you send thousands of bytes in the same sequence, TCP makes sure that you will receive these thousands of bytes exactly in the same sequence that they were sent. you should not be naive. Well, if the connection is broken, TCP can do nothing about it. Like if you connect two computers with a wire and you cut this wire, well, you cannot have a reliable connection. There is no connection. But in a case that a connection is possible, meaning that the physical things are working, you can have a reliable connection using TCP. Well, how TCP work is data are numbered, specifically bytes are numbers. So you do not number messages, you number bytes. And you guarantee in sequence delivery in byte. The other thing that there is an interaction between sender and receiver. We'll see more. We already see. Well, there is a handshake part. They synchronize their sequence numbers. The sender says that, well, I want to send a sequence of 15,000 bytes, and this is the sequence number that I use, so such that the receiver knows what are the sequence numbers that it should expect, and it could detect losses and guarantee this in sequence delivery. And there is even more. There are feedbacks that the receiver sends some feedback to the sender, some acknowledgement. So there is a connection between these two. One thing that I would like to say is that, well, about this in sequence delivery. Well, if you send a video and you use TCP, if you use a UDP and send a video, we said that part of this video might be in order. Or for example, the first 15 minutes and the second 15 minutes and the first 15 minutes are not in exactly the same order. And it's up to application to find the correct order by using the playback buffers. Well, it seems weird, well, because we can fix this issue in application layer. Why do we do it here in the TCP, in the transport layer, this in sequence delivery? Because at the time that TCP were implemented, the networks were very small. Well, you have a small networks that you have a couple of computers that were connected via wires. And most of the computers were connected at the MAC layer. When you have some computers that are connected with wire and it's a small network, so there is exactly one path between the two devices, then you have in sequence delivery by the nature. Because if you send some data over an Ethernet cable, data cannot take over each other. So you have in sequence delivery by nature. And people at that time wants to imitate the same thing on TCP. That's why they went through the in sequence delivery. They make sure that TCP does the same thing. And this delivers data in sequence. It's not necessary now. We can forget about it, but you should learn it because we have only one TCP, and this is what the TCP that people use. Let's see an example of how TCP works. So we have sender A and a receiver B. The sender sends a sequence, so sends a packet. This packet is mentioned that what is the sequence, and it is in byte. Well, the sequence is the packet, the byte 8,000 to 8,500. Imagine everything is now received in sequence by B, and that's the next packet. Well, when B receives this packet, since it is in order, since it is in sequence, it will deliver it to the application. Also, B sends an acknowledgement to A that I received this. An acknowledgement is the upper end, is the last byte that B has received properly, meaning that everything before it has been received. So you only acknowledgement the last byte. Whenever A receives this acknowledgement, then they can continue sending. A might send several packets at the same time. Well, in fact, it sends 3 packets, sequence of 500 bytes. 2 of them are lost, and only the last one is received. When B receives this packet, well, again, it will notify the acknowledgement is the last byte that you have received properly. You receive this part, you receive this sequence, but it is not in order. So you buffer, and at B, we will buffer this sequence, and we will wait for the sequence before to be received. So A, again, acknowledge that this is the last byte that I have received properly. But for some reason, the acknowledgement is also lost. Now imagine we are at A, and it's been a time that we haven't received some acknowledgements. What should we do? Well, in order to make everything work, as soon as we send a packet, we associate it to a timer. And if after a time there is no response from the receiver, things will get timeout. We assume at the sender that something went wrong, and we do some retransmission. So at time 3, a timer starts, and at time 8, it is timeout. We'll retransmit the first sequence. Oh, it is received by B. We can deliver this sequence because now it is in order. Well, until now it has received this part, and now it's the next part. It will deliver it to the application and send a new acknowledgement to A. The acknowledgement is now the last byte. It's 9,000. And A retransmit the next piece, this piece here. What happens at B? Well, this sequence is already in queue. Is already buffered somewhere at B. And B receive this sequence. Now it can provide an in-sequence delivery of 1,000 bytes. That's how it's done. In TCP, it's a bit more sophisticated, and we have what we call selective acknowledgement. Selective acknowledgement is like, well, here, 3 messages are sent and 1 of them are received, right? Receiver can send an acknowledgement and inform the sender more, or can say, well, the last byte that I have received properly is this one, but I also received this part. This is called selective acknowledgement. Now on the sender side, you see, well, the things between this number and this number are not received. Now I can send them. With TCP, we said that grouping is possible. So we group these 2 packets together and send them together. It's more efficient. Now, as soon as the receiver sends receives this sequence, now we can deliver the whole sequence to the application because now it's in sequence. Yes. Yes.
In the end, there it would send back an acknowledgement of 10,000.
Exactly. So it's up to here. Well, there is an acknowledgement there. It is shown in the next slide. Well, yep. After you receive this packet, it will send an acknowledgement. So the connection moves on. For TCP sockets, again, we use a socket library. Things are a bit different. At the server side, we create a socket. We bind it to a port number. This port number is well known now. But what we do at the server side, we do listen. And what it does, it hangs the server. It's also a blocking thing. And it waits for connection request. And at the client side, well, you know the information of this server, server S, you know the IP address and the port number, and you do connect. When you do connect, there is a handshake. It's sending a SYN packet, receiving SYN ACK, and sending ACK. It's in principle doesn't have particular information exists in this SYN ACK or SYN or SYN ACK. It's only to inform this server that I'm requesting a connection from you. Now I want to have a connection with this server. At the server side, whenever we receive the SYN, we do an accept. What does accept does? Whenever you receive a SYN packet, the server accepts this request and creates another socket for this communication. This socket is called con. So it's a connected socket. So at server side, we have one socket. It is non-connected. It's only waiting for communication request. The client sends a communication request, and the server accepts this by creating a new socket that is now bound to this client. So this socket is bound to a client, and it is only for this client. So this socket only receives and sends data to this client. As you see, now we do not do send to or receive from. It is a connected socket. You do send and receive. It means that whenever you do send at this socket here, we will send to this socket at this server. Same thing here. Whenever you do receive, it's a packet coming from this client. Why do we do that? Because this is a more typical case. Well, at the servers, you have multiple TCP connections running in parallel with different clients. So what you do, you reserve one socket, is a non-connected socket, waiting for communication request. As soon as you receive a communication request, you create another socket for that communication. Well, why do we do that? Because in TCP, communication is longer and there is interaction between the sender and receiver. So we isolate that connection. Oh, this is how operating system views TCP sockets. For example, when IPv4 packets are coming, we have two buffers. We have two socket buffers. Well, we have one that is a non-connected one. It is for SYN packets to go there. So SYN packets go and will be buffered in this socket there. And whenever there is a SYN packet here, the application will read that and create another socket for that communication. And data go through those pink sockets. Yes.
Different cache for each client, or we still have that we ask the same things?
Well, I don't exactly know what you mean by different cache, but let me answer this. Maybe it's the answer to your question. Well, these pink sockets are created by these blue sockets, and they inherit all the information for this connection. I mean, this socket is bound to a local port number and IP address, and also outside the client's IP address and the socket number. Oh. Was that your answer? Or?
For instance, if both you and me send the same request to the server, are we still creating two separate connection requests and doing it one way? Or if I ask before you, are you going to get the info from the cache?
Well, on the server side, you mean? Well, on the server side, whenever you receive a SYN packet, a connection request from a client, you create a socket for that connection. If two SYN packets coming at the same time, it doesn't matter, you will buffer them. The first one that is arrived is at the top of the buffer. And as soon as the application reads this SYN packet, it creates another connected socket for that communication. Oh, that's the same thing for IPv6. I'm not showing here the dual stack, but that's the same principle. Well, that's a recap on what we said about TCP. We'll call this, what TCP offers, we call it a stream service. UDP is a message-oriented. TCP is a stream service because of this in-sequence delivery. Or, when you send a stream of thousands of bytes, it is a stream service because everything is received in the same sequence at the destination. There is a side effect, it's called head-of-the-line blocking. We already discussed about it last week. Well, since TCP take care of the lost packets, it's by done some retransmissions. Sometimes when you send a packet and it is lost, so everything is now blocked until this packet is retransmitted several times probably and is received by this receiver, and that's called head-of-the-line blocking. For example, if you send 1,000 of bytes and byte number 2 is lost, everything except byte number 2 is received at the destination. The application layer at the destination will deliver nothing because it's waiting for a sequence 1 to 1,000, but number 2 is missing. So until this number 2 is not reached the destination, you deliver nothing to the destination. Nothing is delivered to the destination, and only at the time that byte number 2 is received, then you deliver a sequence of 1,000 bytes. And that's head-of-the-line blocking. That's a problem that we saw that adds delay to TCP. Now time for a question. Well, I'm here showing 3 applications. I'm asking for which one TCP, specifically a streaming service, is a drawback. First one is HTTP protocol, where we use 1 TCP connection per object. What does that mean? Well, when you see a HTML web page, there are different images and there are different videos on that web page, where we use 1 TCP connection per object, per one of these images on the HTML web page. Another thing is that we use 1 TCP connection for the whole thing, for the whole page. And number C is a real-time streaming application, for example, PMU measurements or live streaming. For which one TCP using TCP is not a good idea because this streaming service has a drawback. So I open the poll. I'm closing a poll in a second. Oh, the majority says E, A, and C, which is partly correct. Oh, we already discussed because of this head of the line blocking, its TCP is not preferred for real-time streaming for PMU measurements, for example, because the delay is too large and data becomes too old to be useful. It's better to have a UDP to have real-time communication. Some data might be lost, but we can still use the data. But what about the 2 HTTP protocol that we said? Well, if we have one single connection for the whole HTML web page, again, this head of the line blocking can cause some error. How is that? Well, imagine that you're visiting a web page and there is a video on that web page. Well, this video is a large file. Because of that, you cannot see nothing. You can see nothing because this video is not yet received in sequence and everything, and you do not see nothing on the website. But if you have TCP connection per object, you see the website, but the video is not shown yet. So you can read everything, you can see other images, but it took that video a bit more time to be shown there. And that's one thing we prefer. You see that when you visit a HTML web page, sometimes the image is not yet loaded, but you can see the other stuff. That's why people do more TCP connection per object. Well, let's do a summary of why do we have both TCP and UDP. So what is specifically because TCP is a sophisticated one. Most applications prefer TCP because when you use TCP, you have a reliable connection. It's like you have two computers that are connected with the line, with the Ethernet cable. As I said, TCP emulates that. Well, but why do we prefer UDP? There are 3 examples, for example, here. Well, for voice application or PMU streaming, so I already answered that. Well, the real-time streaming, you prefer to be on time rather than to be too old to be used. Another thing is that an application that sends one message, like DNS. So that's an example. Again, you prefer UDP. It's a single message. You do not go through the complicated stuff of TCP. You send one single message. If you do not receive any request, after a while, the application times out and sends another message. Another example is when you do multicast, because TCP does not support multicast IP addresses, but with UDP, it's possible to send multicast address a message to a multicast addresses. Okay. Oh, and that's the answer. Well, that's it for the first lecture. We will continue at 10:15 for the performance aspect. Oh, thank you. Start the recording. Thank you. Something that I would like to remind you is that for sure, whenever you have a question regarding quizzes and labs, you can come in person to the lab sessions, but you can always use Moodle also. So we try our best to answer you as soon as possible during the working time, I would say. So whenever you have a question, just ask it. Do not wait for a week to come to the lab session or ask your questions. Now we will go some performance aspects. So the first part is really some definitions to fix some ideas, and the second part is a bit more sophisticated. So we use the word bit rates, the rates. Sometimes we omit the word bit. Is the number of bits that are transmitted per time unit. It's measured in bit per second, kilobit per second, megabit per second, or gigabit per second. So that's the thing. There is another word, it's bandwidth. The formal definition is bandwidth is the width of frequency that you sends data. Sometimes you filter something, and there are sophisticated math behind whenever a channel and you're offered the bandwidth. You can find what is the maximum bit rate that you can obtain from this channel, and there are some sophisticated math behind that. In computer science, people tend to use bandwidth instead of bit rate. We say that we have a bandwidth of 9 gigabit per second. What bandwidth is for us is the maximum bit rate that you can achieve through a channel. Here is some practical bit rate. So whether you're using optical carriers, it can go up to number of gigabit per second. Ethernet is also it's now gigabit per second and so on. Time for a small quiz just to make sure that everything is clear. Well, we said transmission time. What's transmission time is when you want to send X bits and you have a bit rate, how much time do you need to send these X bits? Now the question is, I want to send 1 megabyte at a rate 10 kilobit per second. And what is the transmission time? Now I open the poll. I close the poll in a second. So closing. Well, almost a tie between A and B. One thing that we should be careful is the difference between byte and bit. Well, each byte is 8 bits. Most of the time, we prefer to use size of a packet. We say it's 1 megabyte, but the bit rate most of the time is in bit per second. So here, since we have 1 megabyte, is 10 to the power of 6 times 8 bits. Then divided by the bit rate is 800 seconds. Another thing is the propagation delay. Propagation delay is something that always exists and somehow is independent of the bit rate, is dependent on the physical thing that you use to send physical signals over a distance. Propagation delay is whenever you send a signal, for example, this part of the signal is sent at time t0 and the same part is received at time s0 on a distance, on a destination. Difference between these two times is called propagation delay. Propagation delay always exists. You cannot reduce it. There is a limit to it. Well, you can send physical signals at best with the speed of the light. So the best thing that you can obtain is the speed of the light, and the propagation delay always exists. Is dependent of the channel that you use. It dependent on the physical thing that you use, whether it's electromagnetic waves, it is optical waves, it's radio waves. That gives you the propagation delay plus the distance. The rule of thumb is whenever you use copper, you can think that the propagation delay is 5 microseconds per kilometer. Is a rule of thumb. So if you want to go through a kilometers with a copper wire, it takes you 5 milliseconds. Time for another quiz. What is the propagation time around the Earth? That somehow the longest distance exists in the Earth. I will close the poll in a second. Well, the majority says C, which is correct answer. Well, the distance here in this example is 40,000 kilometers, and with the speed that we have for the copper is 200 milliseconds. So that's basically, depending on the distance, propagation delay can be up to 200 milliseconds. Let's take away from this quiz. Here is an example where we have different distances sending data at different bit rates, and we are looking at the propagation delays. Propagation delay is independent of the bit rate. Well, if you improve the channel, well, we can send the data of more bit rate. The propagation delay depends on the distance and the physical thing that you use. It's optical or electromagnetic waves. However, the transmission delay is different. Well, the transmission delay depends on the bit rate that you use. There is another word, throughput. Throughput is the number of useful data bits per time unit. Why do we have throughput and the bit rate? Or why they are different? Because of several reasons. First of all, it's the protocol overhead. Well, what is that? Well, when you send a packet, send the IP packet, it's a UDP or TCP, you add some metadata to this packet. So you don't send only the raw data. You have the raw data, you have the useful data, you add the, for example, IP and IP destination, IP source, port numbers, and some other stuff. That's for everything to work. That's for routing purposes. And they are overhead because at the receiver, you remove all of them and you look at the raw data. And they are overhead. When you send a packet, there are something added to this packet. For example, in a case of UDP, if you send an Ethernet packet, you will add an overhead equal to 53 bytes. So if you want to send 100 bytes, you send 153 bytes. Only 100 of them is useful data. That's why the bit rate and throughput can be different. There is another reason. We have waiting times. Some protocols for some waiting times add some delay to this communication, and that's why you do not see the same thing at the destination. You do not receive data at the same rate that you send at this receiver. You send at the sender, and you see at the receiver. Explain. Let's see an example of these waiting times. For example, TCP use some protocols to recover losses. The simplest one is a stop-and-go protocol. The thing that is implemented currently in TCP is more sophisticated than that, but the idea is like a stop-and-go protocol. What's this protocol? It's very simple. You send a packet, then you stop. You wait for an acknowledgement. The receiver, if receive you an acknowledgement. As soon as you receive this acknowledgement, you can send the other packet. That's why it's called a stop and go. Here we send a message. We receive the acknowledgement of the first packet. We send a second packet, but it is lost. Then whenever we send a packet, we associate it with a timer, and there is a timeout. So after a while, if we do not receive an acknowledgement, we assume that this packet was lost, and we do the retransmission, and this goes on. That's why it's called a stop and go protocol. And as you see, there is a waiting time. Well, the packet 2 might be ready. Packet 2 is ready at this time, but we force it to packet 2 or packet 3 or packet 4 are ready at this time, but they are forced to wait for packet 2 to be recovered. That's the waiting, one example of waiting time that you add, and makes this throughput not equal to the bit rate. Well, let's go through the performance of the stop and go. Here I'm showing you, well, here I'm sending a packet of length L, and the bit rate that I have is B. Well, the time that it takes to send this packet is L over B, using the bit rate B. This packet is sent, or there is a propagation delay, or this is the propagation delay depend on the distance and the wire that you use. Well, I denote it by D, is independent of the size, in fact, independent of the size and the bit rate B. Well, this packet after a propagation delay D is received at the destination, and this destination sends back an acknowledgement. Well, the size of an acknowledgement I denote it by L prime. Well, the time that it takes to send this packet of length L prime is L prime over B, the bit rate, and I denote it by T prime. Well, this is one cycle where we send a packet of length L and we receive an acknowledgement. The cycle is the transmission time of the packet itself and the acknowledgement, plus 2 times the propagation delay for the packet to reach the destination and for the acknowledgements to come back. That's the cycle time. What is the useful bits that we send during this cycle time is the length of the packet is L. At best, it's the length of the packet if everything was useful information. Then we can compute the throughput is the number of useful bits divided by the time that it took, which is T plus T prime 2 times T. If you play with it, is the bit rate divided by something. So the throughput is smaller than the bit rate, in fact. There are 2 parts. One part is the overhead. Well, the overhead in this case is the acknowledgement. The ratio of L prime, size of the acknowledgement, compared to the size of the packet, plus what we call bandwidth delay protocol product. Well, B over L is the delay and the bandwidth is the D. Oh, that's the 2 measure of efficiency that you can use. And this is one example where you can compute the throughput from the bit rate. You see, it's something less. Well, that's an example of when you have some bit rates, what is the efficiency, basically, what is the bit rate times what percentage is your throughput. I say is most of the time it's very efficient. It's even more efficient in the real TCP because we do better than a stop and go, and we're always more efficient. And that's an example that you can go through. Well, let's use. Well, let's go through the second part. It's my favorite part, and it's called congestion control. On TCP, when some sources want to send some data, they cannot send at whatever rates that they like. They should adopt the rate with respect to the network conditions. Otherwise, congestion collapse occurs. What is congestion collapse? Well, at the time that internet were implemented, the networks were not that huge. We have a number of computers that were connected to each other. And the rate that data were sent was not also very large. For example, at October of '86, the rate of the internet was around 32 kilobit per second. With 32 kilobit per second, you cannot do much. You can send an email, but you cannot have Zoom calls as do we have now. What happens in October of '86? This rate of 32 kilobit per second suddenly dropped to 40 bits per second. 40 bits per second is like nothing. You can do nothing about it. Well, they experienced a sudden factor of 1,000 drop, and that was the first congestion collapse occurred in the internet. Hopefully, it happens at the earliest stage of the internet, and it wasn't fatal to that. This congestion collapse occurred not because that people weren't aware of it. In fact, people were aware of congestion collapse, and there were other company networks such as DECnet, which superior at that time, they already thought of some congestion control mechanism to avoid congestion collapse. Internet was not one of them because people didn't care. They implemented things, it worked, so they didn't care until it collapsed completely. Let's take a look at what really happened at October of 1986. Here I'm showing a small example. It's a toy example, but it's not far away from the reality at October of 86. Here I have source S1 and S2, which want to send some traffic to destination D1 and D2. Oh, source S1 sends some traffic to D1 and S2 sends some traffic to D2. S1 and S2 are connected to this router here with these two links. So for S1, this link has a capacity of 100 kilobit per second. So can be a Wi-Fi connection or Ethernet connection, but has a capacity. You can send at most with a rate of 100 kilobit per second. S2 is connected to this router with a much higher capacity, 1000 kilobit per second. Then we have two routers here that are connected to each other with a rate 110 kilobit per second, and here also 110. Well, the thickness of each line shows the capacity. What are the other assumptions? Well, we assume that we have greedy sources. What are greedy sources? Well, greedy sources send as much as they want, basically as much as they could. Well, how is that? Well, S1, what S1 sees from the network is that it is connected to this router by this link, and this link offers a capacity of 100 kilobit per second. S1 is greedy. Well, S1 will send data at rate 100 kilobit per second because it is as much as it could. Same thing for S2. Well, S2 sees that it is connected to a network where a line that has the capacity of 1000. We'll make use of all of that because it is greedy. So S2 sends traffic at rate 1000 kilobit per second. S1 sends traffic at rate 100 kilobit per second. Well, until now, everything is fine. What is the problem? The problem occurs here. Well, what is the aggregate submitted traffic to this link? Well, it's the traffic coming from S1 and the traffic coming from S2. It is 100 plus 1000. It is 1000 and 100. What the capacity of the link is 110 kilobit per second. So we are submitting 10 times more than the capacity that this link have, which means there are some losses at this point. Well, for sure, at this router, we do some buffer management. So we buffer things to make sure that loss do not occur. But since the submitted rate is much more than the capacity, sooner or later, those buffer will be full and will overflow, and there are some losses. So only a fraction of the incoming traffic to this link will make it through. Well, a fraction of traffic coming from S1, a fraction of traffic coming from S2. How do we divide these losses between S1 and S2? We have another assumption. The loss is proportional to the submitted traffic. What does that mean? Well, in this case, as you see, the submitted traffic is 10 times higher than the capacity. It means that only the 10% of the submitted traffic, aggregate submitted traffic, will make it through. How do I divide it between S1 and S2? Well, it is proportional. It means the 10% of S1 and 10% of S2 will make it through this line. Those are the assumptions. Then what is the question? The question is, what is the throughput of this traffic from S1 to D1? So if I sit at D1, what is the rate that I see the traffic are coming from S1? Now I will open the poll. This is the last poll of this lecture, so don't be shy. So I'm closing the poll in a second. Well, the majority says A, which is the correct answer. Let's see how we compute it. At observation point 1, we should compute what I call ratio of the accepted traffic. What is the ratio of the accepted traffic? We look at what is the aggregate submitted traffic to this link compared to the capacity. Capacity is 110. The aggregate submitted traffic to this link is 100 plus 1000, which gives us 10%. This is a ratio of the accepted traffic at this point here. Since the loss is proportional, so 10% of the incoming traffic of S1 will make it through, and 10% of the incoming traffic of S2 will make it through. So we have 10 and 100 for S1 and S2. For S1 is easy. So at observation point 2, we have ratio acceptance of traffic 100 because the submitted traffic to this link is 10 kilobit per second. However, the capacity is much larger, it's 100. So whatever comes in goes through. So the 10 kilobit per second here will make it to the destination D1. And that's the throughput that this traffic coming from S1 to D1 will take. There's another story for S2. Well, until here, it has a rate of 100 kilobit per second. But at observation point 3, again, we have a ratio of accepted traffic of 10%. The capacity is 10, and the aggregate submitted traffic to this link is 100, which gives us 10%. It means only 10% of this traffic will make it through, and we will obtain 10 kilobit per second for the other traffic also. Well, if you think about it, that's stupid, because if we have a global overview of the network, in the path of the traffic of S2 to D2, there exists a link that has the capacity of 10 kilobit per second. It means that S2 will never achieve more than 10 kilobit per second anyhow. And the fact that S2 is greedy is sending at much more rate, and we will congest this link here and hurt the traffic coming from S1. So if someone has a global overview of this network, could inform S2 that the maximum rate that you can achieve is 10 kilobit per second. So send at 10 kilobit per second, then a better allocation can be achieved, and S1 can send at 100 kilobit per second. That's an example. If you let sources to be simply greedy, that's inefficient and congestion collapse occur. Well, let's see why it is inefficient. Because, well, let's look at this traffic coming from S2 to this router. Well, here we experience a loss, and only a fraction of this traffic, a fraction of these packets will make it through to this link. But of those packets that survived here and make it through this link, again, only a fraction of them will make it through to the destination. So we are using network resources, specifically this middle link here, to send some packets that are useless, that will be dropped anyhow, will never reach the destination. That's why that causes inefficiency, because if we send at a rate larger than 10 kilobit per second, we use this link to send some packets that will never reach the destination and will be dropped anyhow. And that's why it's inefficient. So the take-home message, in TCP, we cannot let greedy resources. Well, we'll see that the problem can be even worse. Here is another example, is another academic example. Here we have a ring network. We have some nodes that are connected in a ring manner, and we assume that we have a perfect symmetry, meaning that each link has the same capacity equal to C. At each node, there is a source that's coming in the network and with the destination exactly 2 hops away. At node I, source I comes in a network, uses the next 2 lanes and goes out in the 2 hops away, node I plus 2. And at every node, we have such sources. Well, again, at this node, this source comes in, use the next 2 link and goes after the network. All these sources sends data at rates lambda. And we have these sources everywhere. So we have a perfect symmetry in this ring example. Well, this link here, if you look at it, it is used by 2 traffic, fresh traffic coming from node I, and a transit traffic coming from the previous node. Well, this link is used by two traffic, and therefore there might be some, depending on the rate, there might be some losses. Well, of the rate that lambda we submit, a fraction of it will make it through. I call it lambda prime. Again, at this link, there is a competition between this fresh source here and this transit flow. Out of this lambda prime, a fraction of it will make it through. I call it lambda second. Whatever lambda second is a rate that reached the destination, because at the end, there is no congestion there. There is no competition there. The question is, what is this lambda second as a function of lambda? Let's go through the obvious case. And the obvious case is where we are below the capacity. Well, the rate that our sources send is below the half of the capacity. In this case, simply there is no loss, because if you look at each link, the aggregated submitted traffic to each link is below the capacity. So whatever comes in goes through. So lambda second is equal to lambda. What if we go behind the capacity? Oh, that's a bit more sophisticated, but nothing special. We can do the math as before. We should compute the ratio of the accepted traffic at each node. And since it has a perfect symmetry, it is same everywhere. If you look at this link here, well, we should compute the aggregate submitted traffic. The offered traffic is fresh traffic is lambda, plus a transit traffic. Transit traffic has a rate of lambda prime. As I said, it's a perfect symmetry. So all the transit traffic has lambda prime, they are equal to each other. Well, the aggregate submitted traffic to this link is lambda plus lambda prime, and the capacity everywhere is C. Well, that's the ratio of accepted traffic at a node. Well, what is the fraction of lambda that makes it through this link? Well, this is the ratio of the acceptance times lambda. Well, that gives us the first equality. Same thing happens for lambda prime. Well, what is the fraction of lambda prime that make it through this link is lambda prime times the ratio of the acceptance. Now we have two equations and two variables, or we can solve it. So I already did the math. Oh, that's the thing that we obtained. Oh, if we find lambda second as a function of lambda, this is the function when we are above the capacity. And here I'm plotting it. Well, here on the y-axis, I'm plotting the lambda second, what reaches the destination as a function of lambda, what we submit to this network. When we are below the capacity, things are perfectly fine. We have a one-to-one map, or lambda second is equal to 1. As we increase the lambda second increases in the same manner. As soon as we go above the capacity, the congestion collapse occurs. And you see that we are submitting more and more to the network, but we are receiving less and less. And that's why congestion collapse is. The problem is even worse. If we use the Taylor expansion and use a Taylor expansion of this function, we see lambda second has a form of 1 over lambda, meaning that if lambda goes to infinity, lambda seconds becomes 0. So if you submit submit the traffic at a very large rate, you are submitting nothing in the output. And that is called congestion collapse. Why is that? Well, it's the same principle. Well, at the first traffic that is submitted here, of those fresh traffic, only a fraction of them will make it through this link. So of these packets that are coming to this network, a fraction of them will make it through this link. Of those packets that survived here, were not dropped here and make it through this link, again, only a fraction of them will make it to the destination. So we are using network resources to send some packets that are useless, that we will draft in the next intermediate points, in the next nodes. And we are using network resources for more useless work and less useful work. And the problem becomes worse if we increase the rate. We end up doing more and more useless work. And that's why we see this pattern. We see that the useful work that we do at the end becomes decreasing as a function of the rate that we submit. The thing that we are interested in is to work at this region. This region is a region that we are maximally efficient. And that's done by congestion control mechanism. So on TCP, we would like to adapt the rate of the sources to work in such regions that are maximally efficient and avoid such things such as congestion collapse. So we say that the congestion collapse is a pattern that can occur in any complicated network, and also in a road traffic. You can experience congestion collapse. Is a region that you're submitting more to the system, but you are receiving less. The total throughput decreases. We should somehow avoid it, and that's congestion control mechanism. We should inform sources to adapt the rate to the network status, and that's done in the internet. Otherwise, we experience congestion collapse and inefficiencies. Well, in internet, well, we are using a TCP specifically. Well, let's fix this. In UDP, we do not care about congestion collapse or anything. Well, UDP is the least minimal thing. At source, you say that send data at this rate, and UDP does it. It doesn't care about anything, that packets are being lost or network is being congested. And that's what hurts the internet the most. The UDP sources hurt internet because they do not adopt the rate with respect to the network status. Well, imagine that you have a line, it's has a capacity of 1 gigabit per second, and suddenly, out of a sudden, a UDP source comes at a rate of 10 gigabit per second and uses this line. Because everyone that uses this line, packet losses. And that's the problem of the UDP sources. In TCP is not the case. TCP, we have congestion control mechanism. Well, in TCP, we are using a mechanism, it's called a sliding window. Well, in the stop and go protocol, whenever you can send a packet, you send one packet. TCP is not like that. It's a bit more sophisticated. They're called a sliding window. And it means that you have a window size. And whenever you can send the data, you can send as much as your window size allows you. You can send more packets at the same time. That's the case. And that mechanism is called a sliding window. And TCP sources adjust their window size with respect to the network status. How do we adjust the network size? That's done by tasting the water. So sources start increasing the rate, and they taste the water. They see what happens at the internet. If everything is fine, there is no losses, they increase their rate. They increase their rate until they receive a loss. And whenever they receive a loss, they assume, well, maybe I'm going above the capacity, so I should decrease my rate. And that's a cycle. They're always increasing their rate until they receive a negative feedback. Negative feedback for TCP is a loss. Whenever you do not receive an acknowledgement, you assume something went wrong. It might be due to other reasons, but in TCP, we assume that we are congesting a network and we decrease our rate. There are additional mechanisms to the TCP, to this congestion control. It's called the slow start. Well, it's whenever you have a fresh traffic coming to a network, it starts with the rate 0, I mean, literally very small rate, and increase its rate. And going from approximately 0 to 1 gigabit per second takes a bit time with the method that is done in the internet. They use additional methods such as a slow start to increase this increasing rate, I mean, to make it faster. Well, the mechanism is called additive increase, multiplicative decrease. We will not go through in depth in this course, but what is additive increase and multiplicative decrease? Well, whenever a loss is detected, you reduce your window size by, roughly speaking, by 2. So if you were allowed to have a window size of 5,000 bytes for 5,000 bytes, whenever you see a negative feedback, whenever you detect a loss, you decrease your window size to 2,500. Oh, that's by tasting the water, right? You receive a negative feedback, you assume things went bad, so I decrease my rate. What about the increasing? Well, the increasing is additional. Whenever there is no loss and you receive an acknowledgement, you increase the window size by maximum packet size. Oh, that's why we have additive increase. We slowly increase, but we multiplicatively decrease the rate. We see that UDP sources are a problem of the internet because they do not care about congestion control, and they might be, in a first example that we see, if we have S2 was a UDP source and sends out 1000, that causes problem for other sources. UDP sources sometimes imitate what TCP does. So we have a UDP that is TCP friendly. Roughly speaking, they implement such congestion control mechanism somehow. Well, that's a recap of the things that we said. Well, in the smart grid and industrial networks, sometimes we use more sophisticated traffic engineering is by do some reservation or priority to isolate critical traffic, for example, PMU streaming. You have a network that is used for different reasons, and PMU streaming is critical one. So you want to make sure that those critical ones has some specific quality of service. So you want to guarantee those them. So it's done by using some reservations and priorities for them. And that's it. Oh, that was on the introduction to the TCP-IP. In the next hour, the professor will take over and go through the security, and the text goes on. I had a great time teaching this course, and I would like your feedback to my teaching. So I create a Google form that is available in the Moodle, and I would be happy if you could all go there and provide some feedback to me. It takes you a couple of minutes, I promise, but it's very important to me. Well, that's it. For next week, the next lab will be uploaded tonight. It's on sockets, and it is online, completely online. So you should complete some codes that you provide to you and upload it on the website. And also you should do some quizzes on the Moodle. The grading part is automatically, so as soon as you submit your code, you see what is your grade, and as soon as you submit your answers in the Moodle, you see your grade. It's different from the version 1. Also, you have QuizCom B2, so you should take it, then you're able to access to the quizzes. One thing that I would like to remind you to take QuizCom B1, because otherwise you cannot submit your lab PDFs. So if you do it, if you're planning to do it in the last minute, just take note of that. Thank you very much. So if you have questions, feel free to ask. Thank you.
Learning how the computer network operates. We have to be aware of security. So the goal of this module is not that you become cybersecurity experts, but some of you, many of you, I hope, will be smart grid engineers. And one of the key issues in critical infrastructures in general, and smart grid in particular, is security. So the goal of this module is that you know the vocabulary of security, that you know enough of what authentication, encryption, and so on mean, so that you will be sensitized to it. And when you work with a deployment, then you will not be surprised. And if you're managing something, you will even be careful that all the security measures are taken. Those slides will be posted on the internet and will be available to a large audience. So I take advantage of this large audience to pass some political information. I usually never do that. It's the first time in 35 years of career that I pass a political message in my slide. This message is for all of you who are watching this and are in a country where you don't know the truth about this, what is happening in Ukraine. And so I hope by passing information along, we might eventually do something against the catastrophe that is happening now. We will talk first about a few things of introduction, then we will discuss all those things. So the goal of this lecture is that you know what all those keywords mean, so that when you develop a system that has to do with it, somebody else will be the cybersecurity engineer, but there will be a friction with you. For example, when you deploy PMU software, your PMU streams data to a PDC. Of course, it's much easier to just stream the data to the PDC and forget about it. But then your cybersecurity engineer will come and say, but your data should be authenticated. That's a very minimum. Right? So that means your software will somehow have to live with authentication. Why do we need to authenticate, and what are the side effects of that? That's what we'll discuss. Perhaps you want even it to be encrypted. Encrypted means it's main secret. Why do you want it to be secret? For example, because you don't want attackers to know what the inside is of your system, because one way to attack the critical infrastructure is to first learn how it works. And you can learn how it works by simply getting into the system via installing a man-in-the-middle attack. That's those who do the advanced lab will do. And then once you have a man-in-the-middle attack, if the things are not protected, if they're not encrypted, you will read all the commands that are sent. So if you're an educated engineer, by reading the commands sooner or later, or with the help of someone else, you will know what are the commands that are actively used in the system, which is the first step into mounting an attack. So cybersecurity, a few years ago, we needed to convince people that security is an issue in the smart grid. Surprisingly, not so long ago, I did a project with ABB where they were saying, no, we don't need encryption on the wide area network links. And we showed to them a number of attacks that you can do. Now they do it. Now I think the world has become way more hostile. So everybody knows that security is a problem. The first attack that was done on from the cybersecurity part was consisting in destroying a diesel generator by simply taking control of the control system of the diesel generator. When you have the control system of a diesel generator or a battery, for example, a battery is protected by its battery management system. Right? You always have protections at the physical level, like fuses. Let's pretend if there is an overcurrent, the fuse will be destroyed somewhere and the circuit is open. That's the end of it. But for complex systems, like a diesel generator or a battery, this is not how it works. It works because you have some electronic, which is programmable, so a computer, that essentially takes some actions. For example, in a battery, we decide that the voltage is high enough, we should not inject more because the battery might burn. It's the software that does it. If you take control of the software, you can let the software issue wrong messages that will lead to a fire, to the destruction of the system. So any battery that has a battery management system, if you can control the battery management system, you can put the battery to fire. This was shown in a slightly different context with diesel generators in this paper here. It's called the Aurora Vulnerability. How do you exploit the system? Well, because the system is based on commodity software. We use MATLAB, we use LabVIEW, we'll use libraries for lots of things. We don't typically use software that we wrote ourselves. In particular, if we are a power company, that is not a software company. Google tends to write a lot of software themselves, but you need to be at the scale of Google for that. For the rest of the world, you use software that exists. This software has vulnerabilities. Vulnerabilities are things that allow, for example, buffer overflow attacks, things that are very hard to be sure that there is none of them, but those are essentially bugs. We know it's bugs when we discover them, but when we write the software, it might not always be visible as a bug. There are classical bugs like divide by zero or have a buffer that is out of bounds, and you hope that the computer will do the right thing, but sometimes it doesn't do the right thing. It reads the thing out of the bounds. Now, if out of the bound there is something that instructs the processor to go to a register location that will start some instructions that you have placed somewhere else in the machine, then you can run a program that is not expected to be run. You can also escalate privileges, so you can have privileges that allow you to destroy files or run things that are not allowed in principle. So this is how this was happening here. Your predecessor at PFL, Tech Tesfaye, did a PhD completed in 6 years ago, where he studied, interestingly, an attack that was done on Ukraine's grid. So the first hacker-caused power outage in Ukraine was done in Ukraine in 2015. So you see that this war started, in fact, long ago. It was a long-lived plan, where, of course, we never know when there is cyber attacks. It's not signed, like when a Russian jet comes and bombs you, you know it's a Russian jet. But when a cyber attack comes, there are hints, but it's very hard to know where it's coming from. But the first attack that successfully managed to cut power in a country was a cyber attack. So by gaining control of some elements of the control system of the grid of Ukraine, you could cut power. The good news is that for such things, well, we know how to prevent them to a large extent by using all the mechanisms we will discuss today and next week, but also because in principle you have backups and you have recovery plans that allow you to restart your entire computer infrastructure once it has been destroyed by a cyber attack. Interestingly, a few years ago, we had a web server for the smart grid project of EPFL that was using a Drupal web server technology that was susceptible to SQL injection. That's a type of attack that did happen. So our server was destroyed. In fact, when such a server is destroyed, you cannot recover it. The only hope is you have a backup that is not online, because if it's online, it will also be infected. So recovery plans are important. You must assume that someday your infrastructure will be attacked, will be infected by malware. That means that all your software that is online is unusable. It's infected. You have lots of instructions that are written into it that you might not want to take the time to purge. So the only way is to do a complete reset and have a backup that is from scratch and was isolated, which of course all utilities do today. This is why such attacks are short-lived. You can bring down power for a few days, but by the time the company was able to restore all its software infrastructure, it will come up again. What we will see in this course is the security mechanisms. And again, the goal is that you as power engineers, you're not afraid of them and you accept them, and even you require them if they're not present. But of course, it goes, my message, it goes well beyond. It's not because we have authentication and encryption and certificates that everything is secure. Security is a complete system that has to do with everybody. So in fact, because many systems now are secured with authentication and encryption, the attacks are more social network-based. Social attack means, for example, I have a friend or somebody working in a power station becomes a friend of an attacker. They talk together, they go to a bar, and this friend manages to find the password or a way to connect to the smartphone of the friend if we have two-factor authentication. Or many attacks, in fact, that happened in the past were simply because you had things like, well, there's a simple example that I know of my brother, in fact, he was working at a bank. One day he came to the wrong bank because he was doing short-term replacement. In a village, there were two banks. He went to bank A instead of bank B, and he could log into the system, although he was not even an employee of that bank. But he could log into the system because everything was written there. There was a little post-it because they were used to having people who could come as replacement. And that happens. I mean, if you come to a substation is not manned. There are people who come. If the thing is well organized, there will be very well-defined security measures. If it's poorly organized, there will simply be the password on a post-it somewhere. And anybody who has a vague idea of how things work and is able to break a door to enter will be able to connect. So many attacks that happen are of that nature, which means for that, none of what we see here is important. But nonetheless, we will still see the technical detail. So the short story here is humans and policies contribute to security. So password protection, for example, you should not have a password that is dedicated to a function or to a device, but the password should be that of a human being. Right? If you come to a bank and the password of the computer of the bank is the password of the computer, not of the user who logs in, then this is opening, of course, this is not secure because you can not know exactly who is doing the job. Yeah. So password should be password of a person, and you should never use it twice. The password you use for connecting to this PMU should not be the password you use for your bank account, for example, and you all know that. You should use things like a password manager or a big Excel file that is encrypted or something that to have all your password in a secure place and never use it twice. because any password that you use will be compromised one day. It's just a matter of time. Somebody will find it and post it on the internet. Right? So what you have to think about it, what's the impact for you? If somebody finds my password that I'm using now at TPFL for logging into the system, am I completely stripped off of everything? If yes, then change your password strategy. Otherwise, the effect should be, yeah, my EPFL account is compromised, but not the rest, not my bank, not the the number of the digicode to enter in my house, not the code on my bicycle, etc. So the only thing we can do in security is to hope that when a catastrophe occurs, we are well protected, and also hope that the catastrophe will hit others before us, because there are always, well, it's human, there are always companies and individuals who are crappy and don't do the thing right, etc. So they will be attacked first. As long as there's enough of them, you're less susceptible to attacks. So in order to be in the lot of those people who are well protected, therefore less susceptible to attacks, we need to understand what are the different mechanisms. So what are the goals of those different mechanisms? Well, in a simple communication setup, A and B want to talk together, and there are bad guys like E that want to do something bad to you or to others by means of getting information from you. And the tools, the techniques that the bad guys will use is to try to be in the middle and learn something about what you're doing. For example, as I mentioned, if an attacker wants to take the control of a substation or a power plant, they need to understand all the messages that are exchanged in order to stop something, run, and modify data tables. So if you want to avoid this, this is called confidentiality. You don't want that an adversary is able to learn everything by listening to the channel. Now, as soon as you communicate over the air, you should assume that this communication can be intercepted. You can and have waveform analyzers. You can analyze the Wi-Fi signals. When you use Wi-Fi, then you can easily get all the information. Hopefully, the Wi-Fi that you're sending is encrypted at your source, so that if somebody gets the signal, you will just see a random number of bits. That is what confidentiality is about. But there are other dimensions. For example, you should not be able to modify the message. For example, if A sends a command to B, which is stop the generator, but if the adversary can modify that and instead of saying stop, can say increase the speed, then of course that defeats the purpose of our control. So we want what is called integrity and authenticity. Integrity means the message that we send, when they are received, they are exactly like they were when I created them. They're not tampered with. And authenticity means if I send a message to you, you have to know it's coming from me. Someone else should not be able to send the same message to you while pretending it's coming from me. Because perhaps I'm saying to you, send 1 million Swiss francs to the Red Cross. If someone else sends it again, and you will send twice 1 million, and then my bank account, if I have 1 million, will not be sufficient. Beyond that, if I send a message to you, I want also to verify that when B receives the message, B may want, for in particular financial transaction, they want to verify that you sent it. But of course, the problem might be with an attacker, but it might be also that you are trying to cheat. I say to you, do this, and then you do it. And then I say, oh, I never said to you that you should do that. Why did you do that, you fool? That's also an attack that you can do. Or also that's an attack that can happen when you don't trust everybody. So in some extreme cases, you may not trust everyone. For example, when you have several companies that interact together via the electricity market. We'll talk a little bit of markets. There are other courses that talk about market. When we talk about OPF and demand response, we'll see that. Also, when Swiss Grid interconnects to Romande Energie, for example, there are points where electricity companies connect together to do things. For example, to reduce the voltage on a bus, or to reduce the power on a line, because otherwise there will be an overflow problem, or to increase the power because a generator has an outage somewhere in Poland or in Spain. So if you send such messages, of course, you have to do with third parties who are mildly trusted. You believe you speak to Romain d'Energie, but are you really speaking to them? If you, SwissGrid, you have extremely secure mechanisms and wonderful procedures that prevent you from having any problem, you cannot guarantee that each of the electricity providers with whom you interact have the same level of security. You hope they have, but if they don't have, it will still be your responsibility if you're affected by something wrong that happened because of them that affects you. So you have your own responsibility to protect your area. So you may have to treat with partners that are not fully trusted. So you may want to have what is called non-repudiation or other mechanisms. We will see also that adversaries, so the bad guys, they can be simply passive. They're listening to everything in order to gain information, or they can be active. For example, they can be forging messages, in which case we will need to have mechanisms to prevent forging messages. So here's the first of these mechanisms, which is the most widely used. It's present all the time when we do a Zoom session, for example, when you send an email, it is using that. It is called symmetric cryptography. So that's the simplest of all mechanisms. The goal is to make a message ununderstandable by whoever understands it and doesn't know the secret key. So we have a secret key, which is known by the receiver and must also be known by the destination. So it's called symmetric because of that. The key is the same at two ends of the communicating party. The message, which in the language of cryptography is called a plain text. Plain text means the message, which is not encrypted, is encrypted by using the key. And then by shuffling all this together, we obtain an encrypted text, which is called a cipher text. And this one, we hope, if the system is good, is of no use to anybody. If you just get the cipher text, just a random string of bits, zeros and ones, you don't see what it means. In order to see what it means, you need the key, you decrypt it, and then you get the plain text. Of course, the key must be secret, and the system must be strong enough for what I said to be true here. Let's see an example of a very old system that was used by the time of the Romans. It's called Julius Caesar's Cipher. At those times, very few people could read. Paper, at least in Europe, was not so widespread. I think did not exist. It existed only in China. And so very simple crypto systems could be used like this one. That was enough. Now today, as we will see, perhaps that's not enough. So the Caesar's cipher simply consists in having a key, which is a number between 1 and 26. It's an offset of the alphabet. And then the encryption system, for example, if the key is 3, consists in offsetting the letter by 3 ranks in the order of the alphabet. Here, for example, an A becomes a D, a B becomes an E, etc. So Ave becomes this cryptic thing. Is this a strong system? Well, to see whether it's a strong system, can you decrypt the system? So Julius Caesar sends this message, which is probably carved in stone, transported over horseback by a messenger, and sent to a general. Do you think you could decrypt it? So we're using Zoom. Yes, we're using Zoom, but we're also using SpeakUp, where you can use this room number for this part of the course. Do you see my Zoom poll? Yes. Okay, I try to show the results. I don't see them here. Yes. Majority says C. which is correct. We can analyze here the ciphertext by looking, for example, we see that there is the same letter at position 2 and 4, which is true for this one. It's also true for this one. But then there are other, we should see the same position in those two, the same letter in those two positions, which is not true here. Of course, this cipher is too weak, but still, what you have successfully done here is decrypt a ciphertext without knowing neither the plaintext nor the key. And this was possible because this is a poor cipher that has, first, the key is very small. There's only 26 possibilities. So with a computer, it would be very easy to take this string of letters, shift it by the 26 possible offsets, and look at what looks like a message. So that's an example where the key is not large enough. So here's the brute force attack. I have here all the different shifts here, and we should see somewhere here. So it's not strong enough. Hopefully what we have at the computer today is long enough. So the first thing is the key. The key size should be large enough because we can always do this brute force attack. Here it's also a text that is from the natural language. So the natural language has a lot of redundancy. So if the original plaintext has a lot of redundancy, that can help also to decipher the ciphertext, to decrypt the ciphertext here. But certainly, the key should be large enough such that it is not feasible to do a brute force attack. The brute force attack consists in trying all the possible values of the key, decrypt it, and then analyze the message to see what are those messages that make sense. Because in particular, if they are from a common language. The state-of-the-art system we use today in most systems is called AES, and AES has a key that should be large enough. Today, it's recommended to have 256 bits. With 256 bits, that means the key is a string of that many bits. So there is 2 to the power, if we have 128, which is already the smallest possible size, we have that number of possible keys. So it is not impossible for an extremely strong attacker, for example, for CIA or other large organizations to do such brute force attack. But when you multiply by 2, you square this number. And even then, even if you have all the computers of the world that are working for many, many years or decades, you will not have enough time to attack one single secret. That's how it works today. That's the only guarantee we have today. So we're not sure that when we encrypt that the system is completely safe. We believe, because all the guys that are in the security departments are our colleagues in cybersecurity, and the whole academic community in the world works on that to make sure that the system is not attackable. For example, before AES, there was DES that had keys of 56 bits that was used for many, many years by banking and such equipment, until somebody found that there is an attack that is smarter than the brute force attack. The brute force attack is easy. All you need to know is what is the power of the computer, how many computers can there be in the world, and then you have astronomic numbers. When you put things to a power 2, that quickly becomes astronomic, right? You know that 2 to the power 128 is the number of possible IPv6 addresses. We know it's, roughly speaking, the number of atoms in the universe. So that is a truly astronomic number. So that's one way to go, have a key long enough. But there are also attacks that can be done. For example, if we think of Julius Caesar, I guess you who found the solution did not do a brute force attack. You did not try all 26, right? You simply used some side information that you can have. You know, it must be words of the Latin language. So if you speak Latin, that's even easier. If you don't, even then, you know, it is not a random sequence of letters. So there is information in the message or other information that can make such a system be fragile. Today, we believe that AES with a key of 256 is completely secure. So I use it to encrypt my passwords. And as long as I am told by the cybersecurity community that's secure, I leave it like this. But one day, perhaps it will not be. Not because of the brute force attack, somebody has found a super duper computer, but because there is a secret way of attacking, in some circumstances, some kind of password frame. If your password has twice the dollar sign, then it's visible. And so there might be strange things like this. When that becomes known, you have to change your system. This is why anything that is secure today is not guaranteed to be secure tomorrow, because the security is not mathematically proven. We prove mathematically some properties of a cyber system, but we cannot prove that it will not be attacked. We can simply prove that with all the attacks that have been done today, which of course involve some mathematical modeling, nothing is possible, but this is not guaranteed. In particular, if you think of AES, so AES, the way it works is really ad hoc. So first, it is a block cipher. A block cipher means that we take a message into blocks of 128 bits. Don't confuse the size of the block and the size of the key. So as usual, that's a power of 2, because to be implemented efficiently in computers, that's what we prefer. So if we have a message, we first block it into strings of 128 bits. And then each of the bits is taken as input to the machinery of AES, to which we add a key. And that gives us a block of the same size here. AES is made to be very fast. So it's implemented in hardware, and it's implemented in fraction of a microsecond, so that we can use it for everything. That's the goal of AES. So the way it works is for every key, it does a permutation on the string of 128 bits. So permutation means I take a list of 128 bits, any of this. This number is astronomically large. I cannot write it. So I conveniently use these dots. So imagine that's a thought experiment. You cannot write it. There's not enough atoms in the universe to have enough ink to write it on a sheet. So this list here is transformed. Every block here is transformed to another one, which corresponds to those lines here. And those lines here appear to us to be completely random. Of course, there are more possible permutations than key, because the number of permutation is this factorial. So 228 is already a large number. So factorial of that is even a more astronomical number. But every key gives one unique permutation here. How is that implemented? Well, it's a sequence of blocks that do things like byte, sub, shift, row, mix columns. So a bit like when you shuffle cards, you shuffle the rows, you shuffle the columns, and then you do other operations on the different bytes that represent the order of the columns by using the key and the output of what you've obtained at different steps here. So we will not discuss them in detail. That would be a lecture of its own. It's a bit mysterious why it works. What we say today is that nobody has found a way to break AES. Breaking AES would mean providing information about the plain text, even if the attacker observes several plain text ciphertexts. Of course, if you think of Caesar's cipher, if you have observed a number of pairs of plain text and ciphertext, in fact, if you observe only one, you will know the key. So that's, again, a bad cipher. A good cipher should not have this property. If I observe the plain text and the ciphertext, which an attacker eventually will be able to do, then we should not be able to infer the key. Question?
How do you differentiate in the key what corresponds to the permutation, what corresponds to, because you have, if you change columns, it's one part of the key, if you change rows, it's another part of the key.
Well, it is more complicated than that. So you use, for example, the first, so out of the key, which is 128 bits, so 7 bytes, you have a first mechanism that transforms that into something a bit longer. And then that gives you those 10 blocks here, 11 blocks here. From the first block, you XOR bit by bit the input, and you do those shifting of rows, mixing of columns. So you don't use the key to know which column you shift, but you shift the message that has been XORed with the key. And the result of that, you do it again with another part of the key. And so on. So it's a bit mysterious. I mean, it's ad hoc. I mean, there is not a big mathematical theorem that says you should do this or not. It's just people have tried many things. Similar things were done in DES, and then DES could be attacked. So people have added additional or orthogonal shuffling to prevent those attacks. But the first thing is that we should be immune to what is known the observation of several plaintext ciphertext pairs encrypted with the same key. That's called the known plaintext attack, right? So that's the very minimum you require, or that's the main property you require from any such system. So if you are able to submit to the system some plaintext to be encrypted, you will see the result. With such a system, you will not be able to infer what is the key. That's property of AES. However, AES, like any cipher block system, is immune to chosen plane attacks. What is a chosen plane attack? Well, that's something very simple, where we use the fact that with what we said, the same ciphertext is encrypted to the same, the same plaintext is encrypted to the same ciphertext for a given key. So in other words, if I send you a message like set the set point of the generator to 2 megawatt, I encrypt it, I send it to you or to the center that has to implement it. If I use a block cipher like this one, if I send the same message 2 hours later, the ciphertext will be the same. Which means that if somebody sees the ciphertext again, you know exactly what is happening, which violates confidentiality. So a block cipher alone cannot provide confidentiality, because it's always possible to recognize in ciphertext the same ciphertext that was sent some time ago. Of course, you could say one way to do that is to change the key very frequently, which you can do, and which we do, in fact, but for other reasons, is that even if a ciphertext like this is believed to be secure, if you have seen 10 billion of messages encrypted with AES, it's probably easier to guess that the key than if you've seen only 2 messages. So we try to change key frequently. So AES systems will change the key very frequently. Very frequently means, for example, every hour. Now, in practice, that happens a lot, for example, because when you send messages, there tend to be pieces of messages that are always the same. For example, when you send a message that is a TCP-IP message, there will be part of the header that are easy to guess or are always the same. In particular, if you will be able to know if the header is encrypted, you will be able to know perhaps who sends the message, what is the source IP address, because the source IP address would always be encrypted to the same number. Once you have somehow, for example, if you see the same encrypted thing that comes all the time, you know, well, this is the guy that sends the most messages. Who sends the most messages? Perhaps the PDC. So by this way, you know, the encrypted IP address of the PDC is this. So you can learn information from this, but fortunately, there is an easy fix. The easy fix is to add what is called a nonce. So a nonce is some text that is different at every invocation of the block cipher. So when I use a block cipher, I will use a secret message, of course, the secret key, plus a nonce here that must be different. Now, it doesn't need to be secret if your block cipher is good, is secure, because simply changing this is sufficient to shuffle completely the message here. For example, if I send the same message 20 times, I can add a sequence number to the message. The nonce number can be simply a sequence number. And by adding a sequence number to the message, in fact, the plaintext is different. Of course, this has to be part of the encrypted block. So if what I said about the IP address, if what is encrypted contains the IP source address plus the datagram number, which is incremented by 1 in principle in every IP message, that will serve as a nonce. And in fact, when you will observe as a bad guy, as an adversary who's observing the ciphertext, you will see ciphertexts that are all different. And then that is sufficient to defeat the purpose here. So those are the systems that are used in practice. We use AES. We need a nonce. So one way to use a nonce is by chaining. That gives this AES CDC. So we pick randomly, for example, some initial number, which is called the initial vector. We XOR it with the first block. We encrypt it. And we XOR the encrypted message to the second block. So that is chaining. So that if the messages M here, the plain text, are the same, for example, then the output will all be different, because in fact what is XORed here is the message plus the result of the previous. If you know the key, you can reverse everything, and this XORing can be undone. So when you receive information, you will receive the first message. You need to know the initialization vector. Again, a nonce need not be can be public. Then that will give you, if you know the key, you will get C1. By getting C1, you will get M1, sorry. By knowing C2 and C1, you can know M2, etc. This is called chaining. There is another method that is, which is the one I alluded to a second ago. You simply add 1 to each of the messages. So you have a counter that is incremented for every message. And all you need to know is to know the initial value of the counter. This one is a bit more secure than this one, but both are believed to be secure today. So this is how AES works. And this is our very first building block in our arsenal of security measures. CBS, AES in chaining or counter modes are symmetric encryption schemes with key sizes that must be large enough, but are not very large. There exist very fast implementations because the circuits that I mentioned here, those are very easy. XORing is something that's easy to do, both in software and in hardware. So that was one of the design goals of AES. So there exist very fast implementations. Therefore, because of that, it is widely used today. And as I mentioned, what is secure today might not be secure tomorrow, which is why software must be updated frequently. In fact, that's most of the time when Apple or Microsoft updates or Google updates the software, they say, well, new feature this and that. But if you look in the small characters, there is always a security update. So every software update typically comes with a security update because someone has discovered a weakness in the software. And the fact that you have security updates every few weeks indicate the amplitude of the problem. Right? The software that we have today has enough security problems that we need to fix it every few weeks. Okay, little quiz. So the first statement that I'm making here, and I'm asking you whether they're correct or not, is AES is a block cipher that encrypts blocks of 128 bits. The second statement is AES is invertible for who knows the key. Invertible means if we look at it as a mapping that transforms a block into another block, can we reverse the mapping? I close the poll in a few seconds. And the majority says C, which is perfectly correct. So it's a block cipher, like we said. It's invertible. Well, hopefully, that's the goal. Otherwise, the encrypted thing would not be decryptable by the legitimate destination, which would defeat the purpose. But of course, for who knows the key? If you don't know the key, then you have a random permutation. So your string of 128-bit is any of the 128 possible initial strings, plain text. Yet another quiz submitted to your sagacity. here are 3 statements about the nonces. Which of the 3 are correct? So there are 8 possible answers. I close the poll in a few seconds. And the majority says D, which is the correct answer. The goal of a nonce is A, right? A nonce should never be used more than once in combination with the same key. So that's the idea, to make the initial block always different, because otherwise the ciphertext will be the same. So that's the main property of a nonce. And it's true that it need not be secret. In fact, it's a problem if it's secret, because then it's part of the key and we need to share it. So it becomes difficult to communicate. So typically it is not secret, but it does not have to be random. It is the encryption mechanism that transforms something deterministic in something that appears to be random. So the correct answer is A and B are true. It can be random, but it doesn't have to. We have talked about confidentiality. The next thing to do is authentication, which is very similar and can use similar technology. Authentication can be performed using several mechanisms. We will see some of them next week. This week, we will start discussing what is called a MAC, Message Authentication Code. A message authentication code is also associated with a secret key. Here, there should be the attacker. For some reason, my PowerPoint has transformed my image. When I have a message, my goal is to make sure that if the attacker transforms it, it can be detected. That's what you do when you download software, not from the Apple or Microsoft store, but from somewhere else. In principle, the software comes with a tag, with a MAC, to be sure that the program you're installing on your machine is really the program that you think you're installing from the website that you trust. We'll see how you trust a website later, and not something that has been changed, which of course is the dream of any attacker. Any hacker would like your PowerPoint or whatever small fancy utility you have to transform your thing to PDF or whatever. At the same time, is doing illegitimate thing on your computer. So we know one of the sources of fragilities are installing software that comes from anywhere. That's why the Apple Store and the Microsoft Store and the Google Play Store are so popular, because you want to avoid that as much as possible. Same thing when the PMU sends a message to the PDC. If an attacker can transform the reading, then of course you can, the surveillance or the monitoring application of the smart grid will have wrong information. Will think the power flows, for example, are different than what they really are. So you can burn a line very simply by transforming the PMU measurements, by letting the control system of the grid believe that the power flow on this line is very small. So this control system will, because the control system doesn't know of all the sources, how much power I'm using now, am I boiling tea or not, hot water or not? Of course, the power system doesn't know that. It will simply observe. So if the observation we give is wrong, the power flows may be wrong. The system might, for example, if there is a line breaking somewhere and we need to redirect a power flow, we will redirect on a line that appears to have a very small power flow, but in fact it was not. The line will burn, and then we've lost some assets, and it will take weeks to fix that. So here, the technique consists in having some software that we will explain how it works. Then I take a message, I have a key, and I create a tag. That is the combination of applying the algorithm to M and to the key. And then we transmit the message and the tag in clear text, if we don't care about confidentiality. We can also encrypt, but we'll discuss the combination a bit later. Then I send that to the destination. The destination, who knows the mechanism, hopefully also knows the secret key, will be able to recompute the tag. Now I have both the message and the tag. I apply the same algorithm to the message, and I see whether the tag computed is equal to the tag received. If the tag computed is equal to the tag received, I have some assurance that this message was created by somebody who knows the secret key that I'm using. In fact, that's the only trust I can have. Somebody who knows the secret key. So if the thing is well done, then we will see how to distribute secret keys next week. Then that means that it is a legitimate source here. Of course, we have to be able to say that if somebody creates, the attacker could modify the message, and it should be impossible for somebody who doesn't know the secret key to transform the message and transform the tag here. And now, yes?
You just said that the receiver would compare the tag and check if it's the same as the one sent. But how would you know the one that has been sent?
The one received. So the receiver will receive the message and the tag, and will verify the received message against the tag. So you download some software from a website. It has a tag here. Then you ask your local software to apply like a big hash of your computer program with a key that you must have somewhere if you're, for example, installing the software in a PMU. And then you obtain a computed value of the tag. And you compare that to the received value of the tag. Yeah. If somebody was trying to cheat and change the message, the tag will not be valid. So if somebody wants to cheat, they must recompute the tag and induce you into believing it's right. But the key property of such a system is that that should be very hard to do, or hopefully impossible. Should not be possible for somebody who does not have the key. Here we should say we don't have the key. Should not be possible to recompute a tag for the message. You need the key for that. Voilà, we'll see more details of the Mac next week.